Hi, I'm Bob Hearn. So I'm going to tell you about a puzzle design I came up with last summer. I was going to the International Puzzle Party and I needed to come up with an exchange puzzle. And I kind of had this idea that I wanted to do something four-dimensional, if possible. I didn't know exactly what, but I meditated on this object, which sits on my desk. This is one of Bathsheba's sculptures. It's a perspective projection of a 24-cell. And I had an aha moment then. So this was the basis of my puzzle. Here's what the thing actually looked like for the exchange. So of course there's 5 platonic solids. In 4 dimensions there are 6 regular polytopes that are each made out of the platonic solids. So in particular the 24-cell here, this is the Schlegel diagram or perspective projection that Bathsheba used and that I chose to use as well. There's various other projections one could go with and various other 4-dimensional polytopes. But this one is kind of a nice number. And the reason is the aha that I had is why not make a Soma-like puzzle out of this? Everybody knows Soma. Martin Gardner, of course, wrote about it and says, in my opinion, this has been the most successful 3-dimensional puzzle ever designed. Interesting fact, it was designed by Piet Hein during a lecture on quantum mechanics by Heisenberg. From start to finish, he designed this puzzle, and it became a huge hit. It's not a particularly difficult puzzle. There's 240 solutions. But I wanted to take this idea and just like the cube is chopped up into 27 individual cells, yes?
May I modestly remark
yes.
that I and Richard Guy's son, Michael Guy, were the people to discover that there were 240 solutions.
Thank you. So John Conway and Richard Guy were the ones who discovered, Michael Guy were the ones who discovered that Soma has 240 solutions. So at first sight, there might be a problem here. And why is that? So let's look at the combinatorics. So the Soma puzzle is made out of 27 unit cubes, and they're all identical. Here we have 24 theoretically identical octahedra, but that's only in 4-dimensional space. We're projecting down with a perspective projection into 3-dimensional space, so they're not all shaped the same. Also, one of the octahedra is the exterior, so we can't really use that. There's a unique, tiny interior one that is irrelevant for puzzle purposes. It has a forced position, so that leaves us with 22 cells instead of 27. Plus, they're all very constrained because you see at the top here, here's a very squashed octahedron, which is a very different shape from the spiky one, which is a very different shape from one of these inner ones. And this flat one is going to have to go on the outside. So that seems to me, just thinking as a puzzle designer, this is going to make this puzzle too easy. It's going to be too constrained. You can't make an interesting puzzle. But I sat down to solve this and wrote a search program to enumerate all possible dissections, and I had a few properties that I wanted. I wanted to have unique pieces, distinct pieces, and I wanted to have them go together to form a unique solution, and I wanted for any n, which is the number of pieces in the dissection, to have the hardest instance for that n, and I'll describe what that means in a moment. But you can see this is a tough search because there's about 160,000 possible ways to combine those 22 unit things into pieces that hold together, and I had to search over all possible subsets of those effectively. I didn't literally search over them all. There's lots of pruning you can do. But that worked, and I got the answers that I wanted. And if we can switch to the Elmo. So here's the result. This is the 6-piece puzzle, which I like because when it's solved, it is a math art object. And it also makes a nice puzzle, which is surprisingly challenging. The 6-piece version, and here's what my metric of hardness is. Here's what makes it hard. So there's 6 pieces here. If I pick any 5 of them, they will go together into this octahedral shape in at least, zoom out? Yes, thank you. Oh, that would be even better, wouldn't it? Yeah, yeah. So if I pick any 5 of these, they will go together in at least 72 different ways. So if you're assembling it by hand and you think, oh, there's just 1 piece left, you're probably out of luck. That metric doesn't really capture human intuition and reasoning, but it seems to do a good job in practice. This is a very difficult puzzle. It took me several days to solve. The one I used for the exchange is the optimal 5-piece dissection. This one, if you take any 4 pieces, they go together in at least 58 ways. And that's sort of a nice medium difficulty puzzle. Works pretty well. Now if we could quickly go back to the screen. So I learned something out of this. I had a sort of a post-aha. Here is a simple recipe for coming up with fun new ideas in recreational mathematics. Just take any two things Martin Gardner ever wrote about, like say Soma cube and 4 dimensions, and try to work at the intersection of that space and see what you get. So this is my octuplex puzzle from that. My exchange gift is another instance of that. I started with peg solitaire and coin puzzles, and that leads to this thing that you'll get in the exchange. So this suggests you could go on forever. What happens if you try to put polyominoes together with cellular automata? What happens if you try to put Penrose tiles together with time travel? So there you go. There's your recipe for doing interesting stuff. And I'll stop there.